So good day to all of you. This is the chapter 5 of my thermodynamics 1. Chapter 5 is all about the processes of ideal gas. As we can see, or as we refresh our minds on our chapter 3, which is the ideal gas, that is the laws governing ideal gas systems. And now in this chapter 5, we will deal on the processes of ideal gas. There are 5 different processes of ideal gas, which is the isometric, the isobaric, the isothermal, the isentropic, and the polytropic process. Now, the first process in ideal gases is its constant volume, or the isometric, or the isochoric, or the isovolumetric process. Now, in the problem, when we say the problem is in isometric process, it is understood that it is a constant volume. Now, an isometric process is a reversible constant volume process. A constant volume process may be reversible or irreversible. Now, an isochoric process is also called isovolumetric process. It's a process during which volume remains constant. The name is derived from the Greek word isos, which means equal, and chora, which means place. If an ideal gas is used in an isochoric process and the quantity of gas stays constant, then the increase in energy is proportional to the increase in temperature and pressure. Take for an example, a gas heated in a rigid container, the pressure and the temperature of the gas will increase, but the volume will remain the same. In the ideal Otto cycle, we found an example of an isochoric process, where we assumed an instantaneous burning of the gasoline-air mixture in an internal combustion engine car. There is an increase in the temperature and the pressure of the gas inside the cylinder while the volume remains the same. Now, one of the formula in isometric process is in its relation between P and T. Now, this formula, it derives from the ideal gas equation, which is the P1 times P1 times V1 over T1 equals P2 times V2 over T2. Then, since it is in isometric process, we have to cancel its volume since it is in constant volume. So, therefore, all we have left in the formula is P1 over T1 equals P2 over T2. Now, deriving that, we will come up to this equation, which is T2 over T1 equals P2 over P1. Now, in the non-flow work, the non-flow work is equal to its integration of P with respect to its volume. Now, since the volume is constant, we assume that its derivative is 0. So, the derivative of 0 is 0. So, therefore, your work non-flow is 0. Now, change in internal energy. Let's see, delta U, it is automatically that the delta U, the formula for delta U is mCp delta T. Now, please take note in the heat transfer that the CV, that the specific constant that we were going to use is CV, since it is in constant volume. While if it is in constant pressure, we would use mCp. Do not interchange these two constant because you may be get wrong in your problem. Now, your change in enthalpy. Change in enthalpy is delta H equals mCp delta T, since it is the original equation of the enthalpy. Now, change of entropy. When I say change of entropy, your mCv ln T2 over T1. In your calculator, there is a logarithmic equation there. So, all you have to do is to put the values. Now, the reversible steady flow constant volume. As we refresh our minds, as we remember in previous chapters of our thermodynamics 1, we discussed conservation of energy. And that conservation of energy is this, where heat is equal to your change in internal energy plus change in kinetic plus your change in work flow plus change your steady flow and change of potential energy. Now, in the reversible steady flow constant volume, we yield that the steady flow is equal to delta work flow, which is equivalent to volume times P1 minus P2, or just simply P1 V1 minus P2 V2. Since it is constant volume, the volume is the same. V1 equals V2. Now, in a reversible non-flow constant volume, this equation will yield came from this equation. We assume that its potential energy and its kinetic energy is zero, since we're talking about the ideal gases, not the energy. So in irreversible non-flow, your Q equals delta U plus Wn only. And for your reversible non-flow, which is your work non-flow, is equal to 0. Now, for better understanding of the isometric process, we can solve this exercise. Problem exercise number 1. 10 cubic feet of air at 300 psi at 400 degree Fahrenheit is cooled to 140 degree Fahrenheit at constant volume. This is the required, or this is the, ito yung hinahanap natin. So now, 10 cubic feet is our volume. Since it is in constant volume, as you can see here in the problem, at constant volume, therefore your V1 equals your V2. Then your P1, which is 300 psia, and then your T1, which is 400 degree Fahrenheit. Please take note that when you are using your temperature, it should be always in absolute temperature, which means that it should be in Kelvin or in Fahrenheit. And then your T2, which is 140 degrees Celsius. Now, what are the final pressure? Now, when we say final pressure, we are finding the value for P2. So P2 is equal to P1, T1 all over T1. So we substitute 300, it's P1, multiply by it's 600. Since 600 is Rankine, because 300 plus 460 is the conversion from Fahrenheit to degree Rankine. It is equal to 600 all over 860, which is the 400 times plus 460, and 140 plus 460, which is 600, is equal to 900 over 43 psia, or simply 209.3023 psia. That is our final pressure. Now, next, what is the work? Since it is constant volume, we say that in constant volume process, in an isometric process, its workflow is 0. Now, next, what is the change in internal energy? The equation for the change in internal energy is delta U equals mcv delta T. Now, before we proceed to substituting all the constant in our formula, we have first to know or to find what is the value for its mass. So therefore, using the perfect gas equation of the ideal gas, which is PV equals mRT, we can yield to a mass of 9.424494,965 pounds by simply substituting all the values given, which is 300 pounds psi, pounds per square inch. You have to convert in pounds per square feet. So we have to multiply by 144 times 10, which is the volume, all over its R. Its R is 53.3 in English system. Do not forget this value. Multiply by its temperature 1, which is 400 plus 460 equals 860 degree Rankine. So therefore, your mass is 9.42 pound mass. Now, we can now substitute all values in this equation. The internal energy equals mcv delta T, and we have yield to a negative 419.0130 BTU. Now, next, what is the transferred heat? The transferred heat for this is Q equals delta U plus W. Since we obtained already the value for delta U, we can now also substitute the value for delta U and its workflow. So negative 419 plus 0 is equal to negative 419.01 FT. It is okay also to solve using this equation, which is Q equals MCV delta T. It's okay. But since we have already given its delta U and its workflow, we could also use the value or the formula of delta U plus workflow. Now next, the change in enthalpy. The change in enthalpy is equal to MCP delta T. So therefore, we have given our mass, which is 9.42 pound mass, times its CP. Don't forget to remember the values for CP and CV in English system as well as it's in metric system. So 424 multiplied by 600 minus 860, which is the T2 minus T1. And we have yield to a delta H equals negative 588.0885 BTU. Now next, for the change of entropy. When you see change of entropy equals the MCVLN T2 minus T1. Now you can input that in your calculator automatically the logarithmic function of Ln. So your mass, which is 9.42, multiplied by your CV, which is 0.171, and your Ln 600 over 860. So therefore, your delta S is negative 0.5802 BTU per Rankine. So, okay. More problem solving. Now next, the isobaric process. The second process in ideal gases is the isobaric process. An isobaric process is a thermodynamic process in which the pressure stays constant. Delta P is equal to 0. The term derives from the Greek word isos, which means equals, and baros, which means heavy. The heat transferred to the system does work but also change the internal energy of the system. An isobaric process is an internal reversible process of substance during which the pressure remains constant. Now, in relation between its pressure and temperature, this formula is derived also on its perfect equation, the ideal gas equation, which is the P1 B1 over T1 equals P2 V2 over T2. As the problem itself says that it is an isobaric process, therefore it is constant pressure. So we have to cancel out the pressure on both equations. So all we have left is V1 over T1 equals V2 over T2. And deriving this formula will yield a T2 over T1 equals V2 over V1 when we rearrange the equation of the ideal gas. Now next, the non-flow work. Well, non-flow here is equivalent to the integration of PdV. As you can see in isometric, since volume is constant, we assume that it is 0. So therefore, your work non-flow is 0 there. But in isometric, we have values for volume. So therefore, your P will be multiplied into its final volume minus its initial volume. So therefore, your work non-flow is equals to P times V2 minus V1, or just simply work non-flow equals P1 V1 P2 V2 minus P1 V1. Now, change in internal energy. For delta U equals MCV delta T, it's the same. Now, in heat transfer, now as I can recall a while ago that I said that in isobaric process, the specific constant is MECP. While in isometric process, the specific constant is CV. So therefore, in heat transfer, your Q is MCP delta T. Now, in changes of enthalpy, delta H equals MCP delta T, which is the same. Now, in change of entropy, MCP ln T2 over T1. Now, for the steady flow isobaric process, we have Q equals delta potential energy plus delta kinetic plus delta internal energy plus steady flow. So therefore, your steady flow is negative delta kinetic, or just simply work flow is equal to negative delta K, or just 0. Now next, For better understanding of the equation, the problem exercise number 1, a certain gas with Cp equals 0.529 BTU per pound Rankine, and where R is 96.2 feet-pound per pound degree Rankine. Now, here's the tip. If the problem did not state the values for R, it is automatically be on its standard condition, which is 53.3 in English system. Expands from 5 cubic feet and 80 degree Fahrenheit to 15 cubic feet, while the pressure remains constant at 15.5 psia. Now, its Cp is 0.529, its R is 96.2, and what is 5 cubic feet? 5 cubic feet is its V1 and its T1 is 80 degree Fahrenheit, whereas its 15 cubic feet is V2 and its pressure or P1 equals P2, which is 15.5 psi. Now, compute the final temperature. The final temperature, as you can see in the formula, P2 equals V2 times T1 over V1, which is 540 times 15 over 5. Your 540 is your 80 plus 460. Okay, yes. 80 plus 460 times 15 over 5, which is your T2 is equivalent to 1620. Now, in the problem, if the problem do not state what kind of unit the temperature is, it is automatically be in absolute temperature. Do not convert it or do not change it into Fahrenheit or Celsius unless otherwise it is specified by the problem. Okay, now next, what is the delta H? The delta H, the equation for the delta H is mCp delta T, but for us to solve its change in internal energy, we must first get the mass. We have to find the mass first. So using the perfect gas equation, PV equals mRT, we have built a mass of 310 all over 1,443 pound mass. So, substituting that into the equation mCp delta T, we have built a internal energy of change in enthalpy of 122.73368 BTU. Now, in Cp equals CV equals Cp minus R, we have since we need to find the delta U. The formula for delta U is mCv delta T, and the only given value for this problem is Cp. So let's go back to our previous problems, that the equation, that the formula in getting the Cp or Cv is Cp equals Cp minus R, which is 0.529 minus 96 over 2 all over 778. 778 is the conversion factor of BTU into feet-pound. Okay? So therefore, your CV is 0.4053 for 144 BTU per pound Rankine. So therefore, we have accumulated a delta internal energy of 94.0479 BTU. Now, next, the entropy. The entropy, change in entropy is delta S equals mCpL and T2 over T1. So we have values for Cp and we have values for mass. Therefore, we obtain a delta S of 0.1249 BTU per Rankine. And now for the work done flow, which is equivalent to P equals V2 minus V1. Since it is a constant pressure, P1 equals P2. So therefore, your 15.5 psi will be converted into PS pounds per cubic square feet. So therefore, you have to multiply it also by 144, and its volume is 15 minus 5 all over your conversion factor into BTU. So therefore, you have work done flow of 28.6889 BTU. And that's it for the isobaric process. Now, in isothermal process, an isothermal process is a thermodynamic process in which the temperature of the system stays constant at temperature delta T equals 0. This typically occurs when a system is in contact with an outside thermal reservoir and process occurs slowly enough to allow the system continually adjust to the temperature of the reservoir through heat exchange. An alternative special case in which a system exchanges no heat with its surroundings is called the adiabatic process. An isothermal process is an internally reversible constant temperature process of a substance. Now, when we read or when we observe in the problem or when we know that the problem is a isometric process or adiabatic process, it is understood that it is a isothermal process. So in the relation between its pressure and volume, as I can recall also on our previous chapter, the equation for the ideal gas also P1 V1 over T1 equals P2 V2 over T2. Since we're talking about the isothermal process, the temperature is 0. So therefore we can omit the T1 and the T2. So therefore all we have left in that equation is P1 V1 equals P2 V2. Now for the work non-flow, the the integration of PdV, which is the mother equation, we have yield into a P1 V1 ln V2 over V1, which is the work non-flow. Now in change in internal energy, since the equation for internal energy is delta equals mCp delta T, so when you see delta T, the pressure, the temperature is constant, therefore your delta U is 0. Now your heat transfer, WQ equals WN, which is P1 V1 ln V2 over V1. Okay, now in change of enthalpy, your delta H is 0 since delta H is mCp delta T, which is your temperature is constant, so therefore your delta H is 0. Now in change of entropy, your delta S equals Q over T, or simply MRLN P1 over P2, or P1 V1 ln P1 over P2. Since MR is equivalent to your perfect gas equation, which is P1 PV equals MRT. So MR is also equivalent to PV ln P1 T1. Okay, I'm sorry, no. This will not interchange. Only this one. Only this one. Now, this one, P1 P1 is equivalent to MR ln V2 over P1. This also pala, pwede din pala siya. Yes, pwede din siya, which is P1 V1. PV equals, delta S equals PV ln P1 over P2. Now, steady flow isothermal, we have yield an equation of 0. Steady flow, which is Ws plus delta K from PV, which is the constant. So therefore, delta S equals Wn, where delta kinetic 0. We assume that the kinetic energy is 0 here. So your work steady flow is equals to your work non-flow. Now for problem exercises, number 1. During an isothermal process at 88 degrees Fahrenheit, which is the T1, the pressure on 8 pounds of air drops from 80 psi P1 to 5 psi G. Please take note of the pressure difference, which is absolute and in gauge pressure, which is P2. For an internal reversible process, determine the integration of PdV and the work of non-flow process, which is here. The integration of PdV or the work non-flow is P1 V1 ln V2 over V1. Just like what I said, or equal to MR P ln P1 over P2 if there are no values of P1 and V1. So it's okay to use this equation. So your integration of PdV or your work non-flow equals 420.9037 DTU. Now your Q equals delta U plus W. So when delta U is 0 and delta H is 0, your Q is 420.9037 also. Since your delta U, MCV, delta T is 0. So your delta U is 0, all you have left is W, which is 420.9037. Now your delta S, which is Q over T, 420.9037 all over your temperature, which is this constant, 548 Rankine. Please take note of the temperature must be in absolute always, equals 0.7681 BTU per hour. And that's it for the isothermal process. Now, for the isentropic, the fourth process of the isentropic of the ideal gases, the fourth process is the isentropic process. An isentropic process is a reversible adiabatic process. Adiabatic simply means no heat. Please take note of that. When you say adiabatic, simply means no heat. A reversible adiabatic is one of constant entropy. When you say isentropic, siya ay constant entropy. So, relation between P, V, and T, as we go back on the ideal gas equation, P1 V1 raised to K equals P2 V2 raised to K equals constant. So, therefore, you have to memorize this PV key. When we say isentropic, we can read it as a formula of PV key. And in relation in T and P, it's TP kick. When in relation of volume, it's TV key. And in relation in temperature and pressure, it's TP kick. So therefore, for you not to confuse on the equation and for you to memorize the formula when it is when the relation is temperature and volume, it's TV key. When its relation is temperature and pressure, it's TP kick. Okay? So T2 over T1 equals P2 over P1 raised to K minus 1 over K. TP kick. TV key. Okay? Next, non-flow. Non-flow, integrating, simplifying, flying, we have work done flow equals P2 V2 minus P1 V1 all over 1 minus K, or simply, just like what I said earlier, PV equals MRT. So therefore, your MR is MR delta T over 1 minus K. Your work done flow. Now, next, change in internal energy, which is MCV delta T, and also your change in enthalpy is MCP delta T. Now, since heat transferred, as you can see in the description or in the definition, that adiabatic simply means no heat. So therefore, your heat here, heat transferred is 0 in isentropic process. Now, change of entropy is also the same as 0 since it is the isentropic is constant entropy. Now, for better understanding of the isentropic process, this is the problem exercise. From a state defined by 300 psia, which is the P1, 100 cubic feet, which is the V1, and 250 degree Fahrenheit, which is the T1. Helium undergoes an isentropic process to 0.3 psig, which is P2. Please take note of the difference, pressure difference of these two. Now, find V2 and T2. Now, in relationship of P and V, since the problem already give a pressure and volume, so pwede natin gamitin yung TPK. So therefore, pwede natin gamitin yung TPK, pwede natin gamitin yung TPK para makuha yung T2. Now here, this is another relation for the volume and the pressure. The V2 all over V1 equals P1 over P2 over raised to 1 minus K. This is the equation. V2 minus all over V1 equals P1 all over P2 raised to 1 minus K. For us to be able to obtain the V2. Since the problem has a given of pressure and volume only. It is limited into a pressure and volume only. Now next, to obtain a temperature 2, we should use the temperature and pressure relation, which is TPK. So therefore, we have yield a T2 of 211.3481 degree Rankine. Again, it must be in absolute temperature unless otherwise it is stated by the problem na iba yung kanyang gagamiting unit. Now, for the delta H, which is MCP delta T, we have first to find the value of the mass. So therefore, oh my God, sorry, natulo ko yung aking mouse. Okay. So now, for the delta H, which is yield to negative 9694.4850 BTU. Now, in your change in internal energy, which is MCV delta T, we have yield to a negative 5,890.8158 BTU. Now, for your work non-flow, which is P2V2 minus P1V1 all over 1 minus K, or just simply MR delta T all over 1 minus K, which your work non-flow or square root of TdV, you can change it into work non-flow if you want, equals 5,820.1132 BTU. And now, since Q equals delta U plus W, when W is Q minus delta U, which is 0, the heat transfer is 0. So therefore, your work is 5,819.8158 BTU. So your work steady flow would be your work steady flow equals work non-flow. So I say work non-flow, saan yung work non-flow natin? Sorry, di pala siya work non-flow. Lilo ko yung... Okay, so now your steady flow is WS plus delta K. Since delta K is 0, we have given a delta K pala. Delta K is delta K is 10 BT. What is the work of the process? Steady flow with delta K is 10 BTU. So if the problem did not state the value for delta K, you have to make delta K 0. So that's it for the isentropic process. And for the last process of the ideal gas, which is the polytropic process. A polytropic process is an internally reversible process during which PV raised to N equals K. Now, the polytropic process is almost the same as the isentropic process, except for its subscript or its exponent. Since in isentropic it is K, dito naman ay N. Pero the formula itself, it's the same, where N is constant. Your TBK, your relation between T and V, TBK lang din yan, or TPNI. It's TBK and your TPK also. Your K, ipalit mo lang yung K ng N, and that's it. Yun lang din yung kanyang formula. Like for example, this one, your P2V2 minus P1V1 all over 1 minus K. That doon sa isentropic dito naman ay Y1 minus N. So your Cn here, ito lang yung medyo nag-iiba. Your Cn, ayan, sorry, natulo ko. Here, your Cn is Cn equals Cv raised to k minus n over 1 minus n. For you to get the value for Cn, you have first need to know the value of Cv, the k, and the n. It usually stated in the problem, or unless otherwise, we have those standards for values of k, which is for hot, it's 1.3, for it's cold, it's 1.4. Now, next, change of enthalpy, MCP delta T, change in entropy, MCN, Ln T2 over T1. Now, please take note of this is not a MCB, Ln T2 over T1, which is okay. Now, it is MCN, since we deals with the polytropic process. Now, the steady flow isentropic, which is the PdV, or the n times P2 B2 minus P1 V1 all over 1 minus n. So for example number 1, during a polytropic process, 10 pounds of an ideal gas whose R is 40 and Cp is 0.25 BTU per pound R changes the state from 20 psia and 40 degree Fahrenheit to 120 psia and 340 degree Fahrenheit. Determine the value for n. Now, as you can see here in the value of n, we have given P pressures, we have given temperature. So therefore, we can also, by using the P-T relation, we can yield the value for n, which is TP kick, TB kick. So therefore, your P2 all over P1 raised to n minus 1 all over n equals T2 over T1. So therefore, your n is 1.3556. Now, for your Cp equals Cv minus R, since the next problem, since the next required is what is the internal energy, since internal energy is mCV delta T and the only given is Cp, we have need to find first the value of TCP, which is Cp minus R, which is 309 all over 1556. So therefore, your delta U now is 595.7584. Now we do not solve for the value of n using PVMRT because we already have the value given in the problem. Okay. Now next, the change in internal energy. Change in enthalpy, which is delta H equals MCP delta T, which will yield to a 750 BTU. Now for the K, Cp over Cv, as you can remember in our previous topic, that the values or the formulas or the ways in finding Cp and Cv or K is also this kind of formula. So therefore, your K is 1.2589. Now, here is the tip also. If there is no Cp or Cv given in the problem, this automatically be in a standard condition. So you do not need to compute the value of K. But if the problem has stated a different value of Cp and Cv, it is understood that you have to compute for the value of K. Do not assume that it is 1.4 or 1.3, as well as the value of the standard value of Cp and Cv. Now, your Cn equals Cv raised to k, Cv times k minus n all over 1 minus n, which is your Cn is 0.0549. And to solve for the delta S, which is the MCP Ln T2 over T1, we have 0.2543 BTU per hour. Now, for the Q, which is the heat transferred, which is your MCN delta T. So, nasolve na natin yung Cn, which is 0.0541. So, our heat transferred is 162.3 BTU. Now, for the work non-flow, we have MR delta T over 1 minus N, which yield to negative 433.2630 BTU. So for your work steady flow, it's the same. For the work non-flow, delta K is the value for delta K here is not given. So therefore, we assume that the delta K here is 0. Ito pala, sinabi pala dito. If the process steady flow during which delta K is 0, what is WS? What is delta K if delta S is 0? It's the same also based on the formula. And that's it for the chapter 5 of our module, which is the processes of ideal gas. Now, it's very, very easy to understand and to comprehend the problem or the topic, since the challenging part of this chapter is the memorization of the formula, and you have not to be confused on different formula regarding the processes, since it is 5 processes and 7 sub-chapters of different processes. So you have to memorize, or you have to accumulate 35 equations, or just like what we say, the 7 generals. Yun yung sinasabi natin, 7 generals. The 5 processes and its 7 parameters, which is 35 equations. So the challenge of the problem is to know, or is to memorize the formula, and the rest is history. It's very easy. All you have to do is to substitute it by your equation. So I hope you will find it very helpful for you to understand the process of ideal gas. And please stay tuned for more videos regarding our thermodynamics 1. Please like, share, and subscribe also to my YouTube channel. Thank you.